Hello students, welcome to another video lecture on digital signal processing. In this video lecture, we will study how to design an FIR filter using window technique, and we will complete this numerical within 8 minutes. The question states that an analog signal contains frequencies up to 10 kHz. This signal is sampled at 50 kHz. Design an FIR filter having linear phase characteristics and transition band of 5 kHz. The filter should provide a minimum of 50 dB attenuation at the end of transition band. Now let us note down the given specifications. Passband edge frequency is given as 10 kHz. Transition band is given as 5 kHz. Next, we need to find stop band edge frequency. Stop band edge frequency can be calculated as passband frequency plus the frequency of transition band. Therefore, the stop band edge frequency comes to be 15 kHz. They have also given the sampling frequency as 50 kHz. Also mentioned in the question is minimum stop band attenuation 50 dB. Now the given specifications are in hertz. We convert the specification to radians per second by multiplying these with 2 pi. So we multiply the passband frequency with 2 pi. We multiply the computed stop band frequency with 2 pi. Next step is to convert these analog specifications to digital specifications. To find omega p, we multiply omega p with t, that is 2 pi multiplied by 10 into 10 raised to 3 divided by 50 kilohertz, which is given in the question. After simplifying, we get the digital frequency omega p as 0.4 pi. Similarly, we convert the stop band frequency into digital stop band frequency omega s, and after simplifying we get omega s as 0.6 pi. Now the step 1 to design a FIR filter using window technique is to select a window type such that the stop band attenuation of the selected window exceeds the given stop band attenuation. In the question they have mentioned the stop band attenuation should be a minimum of 50 dB, and therefore we select Hamming window to design FIR filter. The Hamming window has a minimum attenuation of 53 dB, and in the question we are required to have minimum attenuation of 50 dB. Therefore, we select Hamming window to design this FIR filter. The step 2 is to determine the number of filter coefficients n. The formula to determine number of filter coefficients is as displayed on your screen. The value of k equals 4 for Hamming window. Delta omega can be computed as difference of omega s and omega p. After substituting the values of k and delta omega in this formula, we get n greater than or equal to 40. Let value of n be equal to 41 so that alpha, which is given as n minus 1 by 2, is an integer. Step 3. Step 3 is to specify the ideal or the desired frequency response, Hd of omega. Hd of omega is given as e raised to minus j omega alpha for magnitude of omega less than omega c and 0 for magnitude of omega in between omega c and pi. Step 4. We have to obtain impulse response Hd of n for two cases, that is for the case n not equals alpha and for the case n equals alpha. The formula to compute Hd of n for both the cases is as displayed on the screen. Step 5. Now we need to compute value of cutoff frequency omega c and value of alpha. Value of cutoff frequency can be computed using the formula displayed on the screen. After substituting the values of omega p delta omega, we get cutoff frequency as 0.5 pi, and value of alpha can be computed using this formula. Alpha equals n minus 1 by 2, and we have computed n as 41. Therefore, we get alpha as 20. Step 6 is to find the impulse response h of n. The impulse response h of n of an FIR filter can be given as h of n equals hd of n multiplied by the window function, and in the present numerical we will be using the Hamming window. Next, we compute the value of hd of n using the formulas discussed in step 4. After substituting the value of omega c and alpha in the formula discussed in step 4, we get hd of n as sine 0.5 pi n minus 20 divided by pi n minus 20 for n not equals alpha or for n not equals 20. And for the second case, that is for the case n equals 20 or n equals alpha, we get the value of hd of n as 0.5. We also note down the window function or the Hamming window function. Hamming window is defined as 0.54 minus 0.46 cos 2 pi n divided by n minus 1. And in the present numerical, we have computed value of capital N as 41. Therefore, the Hamming window will exist for 0 to 40. Next, using the expressions obtained in step 6, we compute the value of hd of omega, window function, and h of n. H of n is given as hd of omega into the window function. Therefore, in hd of omega, we substitute value of small n from 0 to 40 and obtain various values of hd of n. Similarly, we substitute value of small n from 0 to 40 in the window function. Later, we multiply hd of n and the window function to obtain h of n. While computing the value of hd of n, kindly bear in mind the value for hd of n for n equals 20 is already computed in step 6. Therefore, you use that value in this table. Similarly, you tabulate value of hd of n, the window function, and h of n for value of small n from 0 to 40, and this concludes the numerical.